time we'd introduced the idea of an infinite series, and we'd looked at the idea of increasing and decreasing behavior in the sequences. And just a quick review, we came up with two ways of kind of analyzing a sequence in general to prove that it was increasing, perhaps, or prove that it was decreasing. And that was to either look at the difference between consecutive terms of the sequence. So this difference here, an plus 1 minus an, so this is taking some term of the sequence and subtracting off the previous term. Well, if you look at this difference and you compare it to 0, either establish that it's greater than 0, or perhaps establish that it's less than 0, then you will have established the increasing or decreasing behavior. If the inequality goes this way around, this is equivalent to saying an plus 1 is larger than an, so that's going to be an increasing sequence, if that's true for every n, or for every n past some particular point in the sequence. Alternatively, and it's not really a different method, it really is equivalent, but it maybe gives an alternative way to think about it, is to look at the ratio of consecutive terms. Look at an plus 1 divided by an, but there, the comparison you're making is not to 0, of course, but you're trying to compare this to 1. Because if the terms are positive, yes, so this only applies to positive quantities. If the terms are positive, then if this is larger or smaller than 1, that's dictated by the fact of whether the top part of the fraction is larger or smaller than the bottom. So if you manage to show that this is always larger than 1, or it's always smaller than 1, then you can draw the conclusion about whether the sequence is increasing or decreasing. So that was last time. That was our first look at the long-term behavior of sequences. Now, the feature we're most interested in is the feature of convergence, which we're going to be talking about now. There's just one final definition at the top of page 5 there. So this is just really introducing terminology, and that's the concept of a bounded sequence. So a bounded sequence is one which is confined to some finite interval on the number line. So it never varies outside of certain limits. Okay? So formally we can express that as saying that the sequence is bounded if there exists some positive number, capital M, such that the absolute value of the term of the sequence xn is never greater than this bound, capital M. Okay? So that's saying the 2 points on the number line, minus n, minus capital M, and plus capital M, the sequence, if this is true for every n, the sequence is wholly contained within this upper bound and lower bound. And that's what we call a bounded sequence. Okay? It doesn't wander arbitrarily far in either direction on the number line. Slightly weaker conditions, so this is like a completely bounded sequence, or it may be that the sequence might only be bounded above. So maybe you can go arbitrarily far down into the negative number line, perhaps, but it might be bounded above, or it may be bounded below. Okay? So you can talk about upper or lower bounds for the sequence as well. So this term, we'll be using that terminology during this chapter as well. Okay, but now we come to the important one of convergence. So we've hovered around this term a little bit in the introduction. In induction week, we talked about convergence a little bit, and in my first lecture, we talked about how it was important in general in science and mathematical modeling. So this is the concept of our infinite process getting closer and closer to some limiting state. Okay, but here, we're specifically looking at it in the case of a sequence, this list of numbers, our infinite list of numbers. And first, we're going to meet an informal definition of convergence. So we have this number L. So L is going to be the limit of the sequence. And we say that the sequence xn, so this curly brackets here, curly brackets xn is referring to the sequence as a whole object in its own right. So we're saying the sequence converges to the limit L if, as n increases, the elements of the sequence get closer and closer to the limit L. Okay? Which is more or less what we've said before about convergence in general. Okay, so as you look further out along the sequence, x1, x2, x3, x4, x5, etc., look further out along the sequence. If you observe the elements continuing to get closer and closer to some final limiting value L, then we say it converges to L. Equivalently, and this is a nice way of thinking it, equivalently, we can talk about the absolute value of xn minus L getting closer and closer to 0. Okay? Because what is that absolute value of xn minus L? That exactly corresponds to the distance along the number line between the points xn and L. Okay? In general, if you look at the absolute value of a minus b for two numbers, that's the distance along the number line between the two numbers. Okay? So this distance between the sequence element and the fixed value L, if that's continuing to get closer and closer to 0 as you go out along the sequence, then we say it's converging to L. Other types of notation that are used, there's two kind of main ones. You can say xn arrow L as n arrow infinity, except you'd read that in English as xn tends to L, or xn converges to L, as n tends to infinity, or as n it goes to infinity. Try and avoid saying converges to infinity, because infinity isn't a number in the same way as the number L. So you can write it like that. So that's read as saying xn converges to L as n tends to infinity, or this kind of notation is used, and that's read in English as saying the limit as n tends to infinity of the sequence element xn is equal to L. Okay, so it's just two different types of notation used, and these types of notation are in very common use. You'll see them in all sorts of different textbooks, and we'll use both kinds at various times. They're kind of used interchangeably. So these sequences are called convergent sequences, if this is true for a particular sequence. The opposite, or the negative, if a sequence is not convergent, then we call it divergent. Okay? It diverges if it fails to converge. Okay? So divergence is the opposite of convergence. Okay. Hi, my name. We also maybe abuse the notation a little bit by maybe writing things like this, that yn tends to infinity as n tends to infinity. So what's being meant there is that the sequence of values yn will be increasing without any upper bound. Okay? They're getting larger and larger with no upper limit. Then we could say that they're tending to infinity. Or maybe tending to minus infinity. If the sequence of elements are getting smaller and smaller and smaller, decreasing all the time with no lower bound, then we could write it like that as well. Okay. So let's look at some convergent. Let's see our first example of a convergent sequence. And we'll begin with this quite easy to understand one. So here, the sequence element, an, if you like, is just the fraction 1 over n. Now, what happens to 1 over n as n gets larger and larger? Okay. Hope everybody's familiar with the idea that if you have a fraction 1 over something, and the bottom is getting larger and larger in value, the fraction is going to be getting smaller and smaller. Okay. And it's going to continue to get smaller and smaller the larger and larger you make the denominator. Okay, so it's not too hard to appreciate that, that this is converging to 0. Indeed, you can see a very similar thing for lots of other related sequences. Okay, so this graph here, you can produce similar graphs in MATLAB or the system Sage. So here we're seeing a plot of the elements of a number of different sequences. We've got 1 over n, the sequence we were just looking at, which is these blue dots here. And we got 1 over n to the power 6, 1 over n to the power 4, 1 over n squared. They're all squashed down here beneath. You can't really tell them apart and kind of superimpose on each other. The ones above the line are, here we've got 1 over the square root of n, Here we got 1 over the 5th root of n. And this picture is suggesting that, well, they're all decreasing sequences. These ones, you know, are as close to 0 as the picture can show. But these other ones are decreasing. And if you could extend the graph out in, you know, arbitrarily far, you'd see these other sequences, 1 over n, the 5th root of n, 1 over the square root of n, they'd be getting closer and closer to 0 as well. Okay? So any sequence like this, 1 over n to some positive power, it's going to be converging to 0. But now, that informal definition is only kind of good so far as it goes, okay? Because you can already see here that these sequences are converging in different ways, okay? Some of them are converging a lot faster than the others, okay? So although to within the accuracy of the values displayed on this diagram, many of the sequences are kind of already effectively at 0. Okay, they're not exactly 0, but you know, to within the error of the numbers on the diagram, they're already at 0, while others are still miles away from 0. Okay? So things can converge at many different rates. Okay? You can have lots of different rates of convergence going on. Faster convergence and slower convergence. And what isn't captured yet by our definition is any notion of how to handle that, what the rate of convergence is, because all the definition says just that the elements are getting closer and closer to some limiting value. So maybe there's a lot of stuff bundled up and hidden in this phrase, closer and closer. It's a little bit vague, it's a little bit imprecise. So we'd like to improve it. We would like to have a detailed technical definition of convergence that will allow us to describe what's going on here carefully and will allow us to prove that these sequences are converging to 0. I mean, we feel it intuitively that these are all getting closer and closer to 0. But we'd like to kind of technically certify that in a way using a nice definition of convergence. But then just as importantly, if we skip on and look at the stuff in the body of pages 6 and 7, where we're going to be going to are establishing many properties of convergence. So to develop the mathematical theory, we're not just interested in picking out loads of example sequences, loads of particular sequences, and judging which of them are convergent and which of them aren't. We want to build up some systematic knowledge about the concept of convergence itself. Okay, so let's just zip through and read all these results quickly, and we'll be proving most of these. So the first one is about the uniqueness of limits. So this says that a function, a sequence, if it converges, the limit is unique. Okay? So you can't have a sequence getting closer and closer to two different values. But in order to prove that, our informal definition of convergence doesn't seem to have the capacity to prove that. We would also like to prove that every convergent sequence is bounded. That's true. There's a monotone convergence theorem. Okay, we won't be proving that. It requires a lot more concepts from analysis. But that says every bounded monotonic sequence is convergent. So a bounded sequence, we know about. A monotonic sequence is just a sequence that's either increasing all the time or decreasing all the time. It's a useful theorem, which we'll be using that theorem a lot, although we won't be proving it. And then the last result here in this section is what's called the algebra of limits theorem. And this tells us a lot how convergent sequences behave with relation to the operations of addition and multiplication. So if you look at the preamble to the theorem, it says, suppose we've got two convergent sequences, an and bn, and that they have limits a and b respectively. Okay? So the an is a sequence converging to a, the bn is a sequence converging to b. What this theorem establishes is three nice properties about what happens when you build a new sequence out of these two sequences that you have already. So one simple way of building a new sequence is to choose two fixed coefficients alpha and beta and form this combination here. So the element of the new sequence, the nth element of the new sequence is alpha times an plus beta times bn. Okay? This is what's known in mathematics as a linear combination. We'll talk a lot about these things that phrase will come up a lot in the linear algebra subject. So this is a linear combination of the objects an and bn, taking some alpha, some real number, some coefficient alpha times an plus beta times bn. Now it turns out that if the original two sequences an and bn were convergent, then so is this new sequence. And the limit that it has is the obvious one. I mean, what could the limit be other than alpha times the limit of the first one plus beta times the limit of the second? It'd be perverse if the limit was something else, okay? Because you're adding the sequences like this, so we'd hope to see the same kind of process take place with the limits. Okay? But we're going to be able to prove that for every pair of convergent sequences. And then there are similar results to do with the operations of multiplication and division. If we form a new sequence now where the nth term is the product of the two of the respective terms from the other two sequences, so an multiplied by bn. That will also turn out to always be a convergent sequence, and the limit that it has is the product of the previous two limits. And that's really nice. It shows that the same process that works in the construction of the new sequence is the process that works in the limit. And a similar result for taking quotients. Okay? So forming a new sequence by taking the quotient of corresponding terms. Okay, you need some extra conditions that you need to be avoiding zero, both in all the sequence terms there and in the limit b of the sequence that you're putting in the denominator. So that algebra of limits theorem, and we'll be talking about it in detail, we'll be working through a proof of it, that provides, you know, a kind of very good linking of the operations of addition and multiplication and so on with this new concept of convergence. And it shows that convergence fits very well with the concepts of adding sequences together and multiplying sequences together. Forming new sequences using the operation of addition and forming new sequences using the operation of multiplication. So it's a very nice, pleasing result. However, how the heck are we going to prove it if the only definition of convergence that we're working with is this kind of slightly naive informal one, saying that the sequence converges if and only if it gets closer and closer to the limit. Okay. So we're kind of fudging over a lot of detail. Detail to do with different rates of convergence. So this sequence is converging a lot slower than the sequences down here, converging to zero. So we need a definition of convergence which talks about these different rates and which captures aspects of them. Okay. So this is what we mean by our formal definition of convergence. So the formal definition of convergence here in definition 1.6, this is the one that we use to certify convergence, to take particular example sequences. We'll be able to prove that they converge using this improved definition of convergence, and it's also the one that we'll use to establish and prove the properties of convergence that we just went through. Okay, now it's a bit of a mouthful to get first time. There's a lot going on in it, so it does take some work to digest and to fully understand. So let's just have a read through of it. Then I'm going to draw some diagrams and some illustrations here that will help us to think about it. Okay. So this is the formal definition. So this is what we're going to mean when we say that the sequence xn, so remember the curly brackets xn means the sequence as a whole. The whole sequence xn converges to the limit L if the following is true. Now this is the Greek letter epsilon that we see here. And this is traditionally used for this quantity. So the formal definition is, if given any value of epsilon greater than 0, we can always find a positive integer n. Now the subscript epsilon on n is kind of indicating that n has a dependence on epsilon. So different values of different values of epsilon will probably require different values of capital N. So if for every positive epsilon we can always find a value capital N, and the property that that capital N has is that whenever the index little n is bigger than capital N, the absolute value of xn minus L is less than this epsilon. What it's saying is, and I'll spell this out with a picture in a moment, epsilon there is a measure of how close the sequence term is to the limit. Okay? That's what the epsilon is. The capital N is the point at which, when you look beyond the point capital N, every sequence element is close, is as close or closer to the limit as this quantity epsilon. So epsilon is like the degree of closeness, or the limit of closeness of the sequence elements to the limit, and the point capital N is the point in the sequence at which this closeness starts to happen and is satisfied for the whole rest of the infinite tail of the sequence. Now, to understand this more clearly, it helps to get a diagram out, draw a diagram of it, and attach the various elements of the definition to the diagram. So I'll just do this for you now on the overhead. Okay, so this is the formal definition. Formal def of convergence. There's a couple of types of diagram that we might draw for it. So if we think of this diagram where we're tracking the values of the indexing variable n on the horizontal axis, and we're showing the values of the sequence on the vertical axis, so we get this pattern of dots across the page. Well, here's where the various bits attached to the diagram. So L is supposed to be the limit of our sequence. And our sequence is converging to L, but of course it might be wandering around the page, doing all sorts of things, but we want to see it settle down and get closer and closer to the limit. So what the formal definition is saying is for every value of epsilon. Now, where is epsilon located on the diagram? Epsilon is located on the diagram here, either side of the limit L. So you've got L plus epsilon and L minus epsilon. Sometimes epsilon is referred to as the radius of an interval around the limit. And normally we think of radius as something attached to a circle, but the one-dimensional equivalent of a circle is just 2 points either side of the center point. Or the one-dimensional equivalent of a disk, which a disk would be a circle and all the interior points as well. The one-dimensional equivalent of a disk is some interval around the limits L. So epsilon is sometimes referred to as the radius of convergence, or a radius, sorry, not the radius of convergence, this radius around the limit L. And the sequence, the formal definition is saying, well, for every value of epsilon, so if someone throws an epsilon at you, there must, if this sequence is going to be a convergent one, there must be some point after which the sequence elements are always within that distance epsilon of the limit. Okay. Now, as suggested in the diagram, that value of n would be located around about there. Okay? Because before this value, n epsilon, some points of the sequence are not within the distance epsilon of that. Okay? They're further away from L. They're right here. However, every point of the sequence, at least as drawn, I mean, we're only seeing some parts of the sequence here, but The implication is that this degree of closeness continues if we could look at the whole infinite tail of the diagram. But as is kind of illustrated here, from this point onwards, it's always true, or at least suggested as much by the diagram, it's always true that the sequence elements are within this distance epsilon of L. So given this epsilon, this red one here, for every n bigger than or equal to epsilon, we have the absolute value of an minus L is strictly less than epsilon. Every point in the sequence is as close as epsilon to the limit L or closer. But we have to be able to do this, or in order for the sequence to converge to L, this has to be true for every value of epsilon. So then the question is, well, what if someone suggested an even tighter value of epsilon? So what if we asked for an epsilon which is smaller, so a tighter interval around the limit? The formal definition says, okay, well, this is a new challenge. Given this degree of closeness to the limit, I should be able to find some point in the sequence beyond which all the sequence elements are as close as that amount to epsilon. So let's call that first one epsilon 1. And then just to illustrate another one, let's make this one so that value could be L minus epsilon 2, and that would be L plus epsilon 2, so that narrower interval around the limit. Okay, that's going to require a larger n, won't it? Because when that level here, we're talking about this border around the limit, isn't it? So this value of capital N won't work for epsilon 2. Because for epsilon 2, there are still a few points there that are outside of this tighter interval around the limit. So the capital N you'd have to use for epsilon 2 would be somewhere, suggested by the diagram, somewhere around here. So this would be N epsilon 2. But this should be possible. It should be possible to find these points, capital N, for every choice of positive epsilon. And those epsilons can get arbitrarily small. They can get as close as you want to the limit. So the epsilon is like a closeness condition around the limit. And if the sequence is going to be judged to be convergent to the limit, it must, for any particular epsilon, it must always be the case that from some point on, and the point in the sequence might be miles out, might be a huge index, but from some point on, all the sequence elements are within that level of closeness to the limit. Okay. So that's an illustration of the parts of the formal definition. So let's go back to that first example of a convergent sequence, and let's prove that it is convergent to 0 using this formal definition. So this is an example proof of convergence. So this the sequence we're talking about is 1 over n. So it appears that 1 over n converges to 0 as n converges to infinity. Now I'm intentionally switching my index variable to m just to keep you on your toes. It's not just some sadistic wish of myself, but you know, when you look in the text, people don't always use n for the index. N and m are common values to use. Sometimes I and j are common values to use. Sometimes when you're considering a bunch of different sequences together and you're trying to deal with them in the one argument, you have to use different symbols for the indices. You have to allow your sequences to be doing different things. So you should never, with all these definitions and concepts, you should not get too attached to the particular letters used in the original definition. You should try and learn them and understand them in a very flexible way so that you can easily switch from one system of notation to another selection of symbol. Okay, so here's the proof of this claim that 1 over n is getting closer and closer. Now, when you look at the formal definition says given any epsilon, there must exist this capital number n. So the way to approach the proof, the way to perform the proof, is to say let epsilon greater than 0 be given. So I just assume that somebody hands me a positive value of epsilon. Now I'm not going to assign an actual value to it, like a half or like a tenth or something very small. I'm just going to deal with it in general. Because the formal definition says given any positive epsilon, there must exist the point n. So I'm going to have to construct an argument here that shows how, given this value of epsilon, how to choose the n. So probably my choice of capital N will in some ways be like a function of epsilon. It'll refer back to this value of epsilon. So just give a little bit, rather than just spitting it out, but just give a little bit of a run-up to it. So we need to make the inequality so it's the absolute value of the sequence element minus the limit less than epsilon for every value of the index greater than or equal to some point. I'm going to use capital M rather than capital N because I'm capital N to mirror the letter being used for the index. Now, I haven't found this capital N yet, but this is what's required of it. So we need to examine this inequality. Now, this inequality simplifies a bit. Okay, it's 1 minus m minus 0. Okay, so that's just 1 minus m in the bracket. Also, we can drop the absolute value signs because n is a positive quantity. N is the index in the sequence. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So it's always positive. So this inequality simplifies a little bit to 1 over n, 0, strictly less than 1 over n, less than epsilon. So this is the question I have to answer now. What is a valid choice for the quantity n? If I can answer this question, if I can provide a valid way to assign a value to capital M that always makes this inequality true in the required range for every little m past this point, capital M, then I'll have succeeded in showing that the sequence is convergent. Then I'll have established the condition in the formal definition. Any ideas or any suggestions or candidates for what the correct value of capital M is? So capital M is supposed to be an integer. It's supposed to be some value of the indexing variable. Well, the role it has to play is it has to make this inequality true. But this inequality is equivalent to 0 less than 1 over n less than infinity, sorry, less than epsilon. If you invert the quantities here, this is equivalent to n being greater than 1 over epsilon. Little n, I should distinguish my little n, my big n's. Little n being strictly greater than 1 over epsilon. So this inequality will be true whenever little m is bigger than 1 over epsilon. Now remember, epsilon is typically a small quantity. It's a degree of closeness around the limit, and it's probably getting quite small because we're trying to show it's convergent to the limit. So if epsilon is small, 1 over epsilon is going to be large. So this tells us how to choose the value capital M. So we will choose capital M to be equal to, let's say, the smallest integer strictly larger than 1 over epsilon. That's what I meant when I said the choice at this point, capital M, will probably be a function of epsilon. It will probably depend on epsilon. And you can see that. Because the rule for choosing capital M is based on what the value of epsilon is. That's okay, because epsilon was given to us at the start. We're trying to build an argument that works for every value, every positive value of epsilon. So whatever the value of epsilon is, if we choose our point in the sequence capital M, okay, it doesn't have to be the smallest integer, but that's the kind of nicest choice. That's the most cleanest, efficient choice. If I choose it to be the smallest integer that happens to be strictly larger than this quantity. Now, typically, if epsilon is a tiny quantity, close to 0, 1 over epsilon is going to be a large quantity. But there will be a smallest integer that is larger than this quantity. If capital M is that point, so i.e., capital M is satisfying this quantity, strictly greater than 1 over epsilon. So for every value of the index capital M which is larger than or equal to capital M, the inequality. Now I'll go back to the original one now. See, these inequalities I got down here were equivalent to the original one, but the original one is the one that best fits the definition of convergence, because we see it as the distance between the sequence element and the limit is less than the required value. So for every value of the index little m larger than capital M, this inequality is true. So that, what I've done there is confirmed that the condition in the formal definition of convergence is true for this sequence. Given any positive value of epsilon, so right to the top of the page, given any positive value of epsilon, there does exist a point in the sequence capital M, and I've described how to choose it here. To show that something exists, you have to show the rule for constructing it, or show that there is a legitimate choice. So this is how you choose your capital M, and that has the required property. For every value of the index past M, the required inequality holds. The element of the sequence is within the distance epsilon of the limit. Okay, so that's our first proof of convergence using the formal definition. Any questions or clarification that you'd like me to provide on that? Now, it is something which, if you've never seen it before, if you've never seen the formal definition there on page 6, if you've never seen that before, it is a bit of a mouthful, and it does require some thinking about to fully see what all the parameters are doing. Thinking about this kind of diagram can help. It helps to picture where the various elements are. So your index is here, the sequence values are on the vertical axis. So the limit is a value on the vertical axis. The epsilon is the distance around L that you're asking for. Now these points in the sequence, well, these are some fixed points in the sequence along here, and then every time you're past that fixed point, some degree of closeness is supposed to happen. Okay. That kind of picture, that kind of way of thinking about it will help you, understand what the definition is saying, rather than just seeing it as a kind of string of symbols on the page, but actually know what the various bits of it are. And this pattern of a proof of convergence is, you'll see this pattern appearing quite a few times. So we're trying to prove convergence. So we have to prove that a certain point exists given any value of epsilon. So no matter what value of epsilon you throw at me now, all I have to do is feed it into this formula, choose the appropriate m, And I've shown that the required inequality limit. So I've proved the convergence. Okay, maybe we can jump in now and, I was thinking of jumping in and starting to prove those properties of convergence, but I think I won't, actually, because I'd rather give a whole lecture over to proving most of those. What I would like to do is introduce you to the next set of tutorial questions. Okay. Are there any last queries on this one? Because we do have a few minutes. Is there any bits of that argument you'd like me to clarify or explain why I did what I did at that point? Okay, you'll find the scan of this page. I mean, I hope you've been taking your notes. It is good practice to take your own notes. But I will put the scan of this page in a comment under the YouTube video for the lecture. So you'll find it there. So let's have a look at the problem sheet. So I think for last week's tutorial, I had suggested questions 1, 2, and 3. Now, you mightn't have completed all those, but you know, we do work on completing all of those and getting satisfactory answers out to all of those. But what we've done today opens up this next section of questions, which is, I mean, you can go ahead and start trying to do some of these, but I'll probably prepare these ones in this week's lecture. There's these 3 questions here. Now, the first question, number 4, is kind of a reflection or discussion type of question. It's just prompting you in various ways and encouraging you to continue to think about this formal definition of convergence until you're quite happy with it. So it's, well, you know, one thing you should be aiming to do is to be able to quote it accurately from memory. Should be able to reconstruct that kind of diagram I drew there, or some equivalent diagram, meaning to be able to take those parameters in the definition and to be able to know what role each of them is playing, to kind of put it together in some kind of sensible way. And also, although they're nice and they're traditionally used for this purpose, don't get too attached to these particular symbols, xn, n, and epsilon. You want to work and understand these definitions in a way that's independent of particular levels. Because they don't have any meaning. All these things are just different kinds of labels, so we can distinguish different labels and talk about different objects. They don't have any inherent meaning. They are traditionally used for various things. Epsilon is traditionally used for a small quantity, n is traditionally used for an indexing variable of a sequence and so on. But that's just only tradition and custom. Questions 5 and 6 are more kind of problem-solving questions. So question 5 asks you to prove the convergence of this sequence 1 over n squared. So that's kind of related to the proof we did for 1 over n. So you should be able to construct a proof that 1 over n squared is convergent. It's going to be convergent to 0. And the proof should work along similar lines to the one we just did there. Question 6 is an interesting kind of question. It's not a question that just has a number as an answer or something. It's again getting you to think very carefully about the definition of convergence and to interrogate your own understanding of it. So the way I thought about question 6 is, I've got 2 statements here, S1 and S2. And if you like, one way of thinking about it is, these are 2 possible ways you might misremember the formal definition of convergence. The formal definition of convergence, it's very, in some ways, it's very sensitive or brittle. Okay? There's various things said in various orders. Given any epsilon, there exists a capital N such that, and then there's some inequality statement depending on the epsilon and the n. Now, the order in which they're said, the epsilon comes first, and it says, given any epsilon, there exists an n. The use of any and exists is also very sensitive to where they occur and the symbols they're attached to. So in S1, we have a statement, there exists a real value lambda, okay, I'm using lambda instead of epsilon. There exists a real value lambda and a positive integer m, such that for all m greater than m, the absolute value of ym and this supposed limit is strictly less than lambda. Now that's an incorrect quote statement of the formal definition of convergence, because it's saying there exists a real value lambda, whereas in the formal definition it says for any real value lambda. Okay. Statement S2 is a similar kind of mixed up version of it. It says there exists a capital M greater than 0 such that for every real value, or for all real values lambda, if little m is larger than capital M, then the same inequality holds. Okay. The inequality appearing at the end is the same structure as the inequality in the formal definition of convergence. So the task here is, well, first of all, to recognize that these aren't the formal definition of convergence. It has to mix some things up a little bit. But to take them on their own terms and see if you can work out or give some examples of certain sequences and certain values that do satisfy those statements. And can you characterize, what are those? So maybe those are definitions of something. Maybe you can characterize, well, the set of, the sequences that satisfy S1 all have this property. And be able to explain it in kind of everyday English or everyday technical English. And for S2, think about all the sequences that might satisfy S2. Can you characterize? Say what kind of features they have. If the formal definition of convergence, all the sequences that satisfy that, the one in definition 1.6, they are all the convergent sequences. They are all the sequences that get closer and closer to some final limiting value L as you go further and further out the sequence. So coming to an understanding of question 6 there will be a very good way of interrogating all the different ways that you can arrange these kind of phrases for every epsilon, this and n. What if you mix them up and arrange them in a different order and so on? What the consequences of that are. So I think those questions 4, 5, and 6 are on the cards for this week's tutorial, whether it be tomorrow evening or on Friday. And the later ones, question 7, and then all these ones on the opposite side, those will be opened up, I guess, after next week's lectures, after we've done some work with the properties of convergence. Okay, any final questions or last questions before we end it? Okay, so Saeed should be here at 10 to start his lecture, so take a break before then. If somebody could bring down the signature sheet, whoever has it there.